everyone. So today we're going to be going over the 2019 AP Physics 1 free response question, more specifically number 2, which represents our qualitative-quantitative translation problem that we are going to see on this year's AP exam. So let's go ahead and take a look at the problem. This problem explores how the relative masses of two blocks affect the acceleration of the blocks. Block A of mass m sub A rests on a horizontal tabletop. There is negligible friction between block A and the tabletop. Block B of mass m sub B hangs from a light string that runs over a pulley and attaches to block A as shown above. The pulley has negligible mass and spins with negligible friction about its axle. The blocks are released from rest. A, subpoint I. Suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. Briefly explain your reasoning without deriving or using equations. I know that some people are going to be happy to see that you don't want to do any deriving here, but let's go ahead and set up the problem as we have it on the, actually on the problem. Okay. Wow, that's ugly. So you've got block A here, you've got a pulley, and you have block B here. And so our first situation is where the mass of A is way, way greater than the mass of B, okay? And they want us to figure out what the acceleration would be. And this one you really don't have to overthink, okay? Don't get into these crazy, don't even think about the free body diagram yet, okay? Which is not something I would usually say, but don't think about it right now. You'll think about it eventually, but not right now. What you're going to do is you're just going to think about it conceptually. If you have a really, really heavy mass on the table and you have a much lower mass that's hanging from the pulley, is the mass going to move that's on the table going to move all that much? And the answer is no. Okay, so whenever we answer the question, we would say that the acceleration is close to zero. Due to A having a greater mass and inertia. Inertia is important here, right? Because we want to explain exactly why the block isn't going to move. It's all well and perfect to talk about its mass, and in fact that's exactly what affects its inertia, but we want to specifically address the inertia because that's what relates to its motion. So since A has that greater mass and the greater inertia, we know that little b isn't going to be able to move it that much. So due to large difference, system's acceleration close to zero. And I'm just kind of repeating myself there. On the actual AP exam, you can be a lot more terse with your response as long as you address the fact that, one, you of course want to tell your answer, right, that the acceleration is close to zero. And you want to give your reason, which is because A has a greater mass and a greater inertia. I just wanted to explain it a little better because, you need the explanation for it, otherwise you wouldn't be watching. So let's go ahead and move on to part 2 of this problem, where we're going to be looking at B having a way, way larger mass. Go ahead and get this down if you need it, and I'm going to clear the board. Or maybe I should, whatever. I've committed. So now we have part 2 where the mass of B is much, much greater than the mass of A. And so if you think about this conceptually again, you're going to come to the conclusion that the acceleration will be very close to the value of g, or the normal acceleration due to gravity. I always like to write complete thoughts. So now I'm actually going to, at least with my answer, I got into a little bit about how the forces actually start to come into this, right? Our acceleration is going to be pretty close to g, what it would be if block B was in free fall, right? And that's because the mass of A is so small compared to the mass of B. If you have if you have a tiny ping pong ball attached in A and you have a lead ball in B, of course the mass of the ping pong ball isn't going to matter that much, right? That's just conceptually you understand that. Here in my answer, I actually involved the tension force because we know that the tension force that's acting on B is going to be due to A. And that's what we're going to get into in part B, where it's going to want us to actually draw the free body diagrams. So let's go and take a look at that. So now suppose the block's mass is much greater than the other, but they are not necessarily equal. The dots below represent block A and block B as indicated by the labels. On each dot, draw and label the forces, not components, exerted on that block after release. Represent each force by a distinct arrow starting on and pointing away from the dot. So never, ever, 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 ever put your components on the free body diagram, unless they tell you to, which they won't. Of course, we don't necessarily have components in this case, but if you had a situation where this was an Atwood machine on an incline, you would have components that you have to split into their X and Y directions, and don't put that in the free body diagram. No, wrong. No bad wrong. Don't do it. So we're going to draw the free body diagrams now, where we're going to take A, and we're going to take B. So again, for the third time, I'm going to draw my Atwood machine. Okay. Since A is resting on a surface, I know that A will have a normal force exerted on it. The normal force is always perpendicular to the surface that the object is resting on, and it points away from the surface. So since my surface is right here, my normal force is going to be pointing up. Wow, that was terrible. Let's get a redo on that one. Less terrible. Okay. And since the block isn't, shooting off into space, I know that it has some force that's counteracting that normal force. Our favorite force that keeps us all grounded, literally, our gravitational force. And I do know that the block is being pulled, it's being accelerated in some direction. I go and look at which direction it's being accelerated in, and I see that it's having a force applied that's dragging it to the right. So I have I'm going to label this tensional force because it is the tension due to a string that's attached to it. And that's usually what we call the tension due to a string. Force due to a string, my bad. So B, we also have the force of gravity acting on it. Never just put G, okay? Because G represents acceleration. You need to label forces on your free body diagrams. And since we have that whole system accelerating, we have that block's force due to tension acting upwards. And that's it. Those are your free body diagrams for this whole system. Don't overcomplicate things. Just determine what forces are there. If you know what forces are acting, then you're perfectly fine. The only non-contact forces you're going to be dealing with are, of course, your gravitational force, and you have electric force, which we're not covering at all on this exam. So really the only non-contact force you have to deal with is gravitational force. So let's go ahead and take a look at part C now that we've got our free body diagrams. So part C says derive an equation for the acceleration of the blocks after release in terms of m sub A, m sub B, and physical constants as appropriate. If you need to draw anything other than what you have shown in part B to assist in your solution, use the space below. Do not add anything to the figure in part B. Well, you don't need to add anything to the figure in part B, but let's go ahead and derive our equation for that scenario. So just remember, actually I'm going to leave these up as we I'm going to leave those right there as we go ahead and derive the equation. So I know that I'm solving for the acceleration of the system. okay? And you may be thinking, okay, well, I have this equation memorized, so I'm just going to go ahead and like write down the memorized equation that I have. And to that I say, okay, good for you, but make sure that you show the steps to how we got to that derivation, okay? And I'm doing what's called a whole system solution, meaning that what I'm doing is I'm taking the force that is, well, the object that's responsible for the force that's dragging the system down for its acceleration and comparing it to the whole system. So whenever we're solving for the acceleration, we know that the acceleration is equal to the sum of forces, or our net force, all divided by the mass of the system. Well, the mass of our system is just m sub a plus m sub b. The reason that it's the mass of the whole system is because both objects are accelerating in the same direction. With a with a regular outward machine, you have the two objects going in opposite directions. You have one being pulled up and one being dragged down. So in that case, since the forces are going in opposite directions, you're going to be subtracting those forces from one another. But since we have both blocks moving in the same direction, right? If A rolls off the table, it's going to be dragged down. Force of gravity acts in the same direction for both, and that's what causes the acceleration of the block system. So our net force is our, if you write something like this, and you don't explain it, like, you're still going to get full points for that. But the reason that I write m sub b times g is because the force of gravity on B is the only thing that's causing acceleration of this system, okay? You don't have to include anything about A. Yes, I know A is moving. A is having a force applied to it. But why is it having a force applied to it? Well, that's because the force of tension is acting on it. And that force of tension is because B is just moving straight down due to gravity, okay? B is pulling on A and dragging it along with it. So that's the net force on our system. And this is, this is our derivation. Like, we are good to go right here. Like, that's it. And so part D asks us, okay, does this follow along with our answer for part A and number 2? And that was the situation where we had the mass of B way larger than the mass of A. And I would say, yeah, actually, you can, and they will award you points for this. If you justify your answer on this one, and you say that, no, you can't actually apply it to what we said for A2, they'll give you points. Now, that's not the approach that I would take, because we already proved in A2 that the acceleration of the system would be very, very close to g. So we're going to go ahead and address that. We said on that one the acceleration of the system is approximately g. So I would say yes, this can be applied to our situation. And that's because if the mass of A is very low and negligible, again, think of the ping pong versus the lead ball situation. The equation becomes there we go. We just proved it with our derivation. And you could actually use the derivation to prove that no, it can't be applied to the situation because you have the mass of the entire system affecting the acceleration of the block system. Like, that's what's great. If you have the correct derivation, as long as you justify your answer, you'll actually get credit no matter what. Okay, but you have to have the correct derivation, so make sure you understand how to sum your forces and what forces are actually causing acceleration of the system. So, last one. We have, While the blocks are accelerating, the tension in the vertical position of the string is T sub 1. Next, the pulley of negligible mass is replaced with a second pulley whose mass is not negligible. When the blocks are accelerating in this scenario, the tension in the vertical portion of the string is T sub 2. How do the two tensions compare to each other? Well, let's go ahead and think about how that would actually affect our system. So, our acceleration for the first scenario we knew was B times G all over M sub A plus M sub B, okay? And now, and of course our force due to tension was some number, right? Now we have an acceleration that is, again, M sub B times G, but now we've added in the masses of the pulley acting on the whole system. Okay, if the pulley's mass is not negligible, then we need to include it as part of the system. So what does this actually do to our derivation? Well, we see that the number in our denominator is increased, right? So if I had, for example, in this scenario, let's just assume that I have 1 over 4, and this now becomes 1 over 5. Well, which one is the smaller number? This one. Okay. But that doesn't answer my question yet. My question was, which one has the greater tensional force? Okay, meaning that whenever we did our free body diagram, right, which one is going to have a larger force opposing the motion of block B? And our answer to that is going to be I'll say T2, and it's greater than T1. The reason being is what we proved up here. If the mass of that system increases, the acceleration of the system decreases. Inversely proportional relationship. Now, if A decreased and M sub B stayed constant, which it was, it didn't tell us that it changed, then the force opposing the force of gravity pulling it down must be larger. And that's why T sub 2, whenever we added the mass of the pulley, is going to be greater than T sub 1, where we did not have mass with our pulley. If you have any questions, make sure to let me know. Until then, have fun studying and be well.